Greetings, Astronomy 10, and welcome back to your first of two Chapter 10 lectures. We're going to be talking about stars for the next couple of lectures, and that really is our next piece of this universal puzzle. So far, we were able to describe, by first proposing and then looking for analogs of, a model for star formation. And we were able to show that our model matches up pretty well with the physics in theory and the evidence in practice in our own solar system. And so for us to take it a step further, we need to try to figure out what the characteristics of these stars in our neighborhood, our galaxy, other galaxies, and indeed the rest of the universe are, before we can try to populate these galaxies and clusters and so on with these stars. We have to know what they are, how they work, and so on. And so the question then becomes, are all stars the same? Are they different? And what makes stars different? What kind of ranges of properties do they have? Now, there are going to be some commonalities, of course. We all know that stars fuse hydrogen into helium, but what we haven't learned yet is they actually only do that for about 90% of their lifespan. So first we want to figure out what the defining characteristics of various stars are. So what makes one star different from another? Now, doubtlessly because we're watching a lecture video here and we're not able to confer with each other in order to try to come to some sort of scientific consensus. Instead, you're probably going to want to just hit pause now and try to puzzle out what the different characteristics of some stars are. Once you're done with that, we'll continue. We're going to go back here to our trusty whiteboard. Many of you were probably able to puzzle out the fact that there are probably stars of different colors, right? We look up at the night sky, we can see some are red, some are, yellow like the sun, and some are actually blue, right? So stars have different colors. Not to sound racist, this is America and everything, but let's not try to anthropomorphize stars. So what else? What is another defining characteristic of stars? Could they all possibly have the same size? Or do they have different sizes? Well, I can conceive of them possibly having different sizes, right? So let's put a pin in that one, and maybe we will learn whether or not stars have different sizes or radii. Right? So the size or radius of a star is a possible defining characteristic. What else? Well, size also begs the question of mass. Do all stars have the same mass? Maybe, maybe not. What about brightness? That's a possible answer, right? Definitely a possible characteristic. Okay. If you've gotten this far, you're doing pretty well. But there is still one missing, and that, of course, is the distance. Some stars appear dim and some stars appear bright, right? But also, if you look deep into the Milky Way with like a telescope, you can tell that there are some stars that are much, much farther away. And so, it would be foolish of us to just automatically assume that all stars are at the exact same distance from us, right? Because that would put them all at the same distance from the sun, first of all. And secondly, that means they would all be attached to the celestial sphere that we were in the absolute perfect center of. And that's geocentric thinking all over again, so we don't want to go there, right? So this is a pretty good set of characteristics. Now, we're not going to get through all of them today. We will probably get through 4 of these 5 today. We'll save some for next time. So of these, Which one seems to be the easiest? Well, we know that they have different colors, we can see that. But how do we define the range of colors and what makes them the way they are? And that may not be the easiest. What about brightness? Well, we need to know how kind of far they are before we know how bright something actually is. If you remember looking at a car's headlights close up and a car's headlights far away, right? The farther away something is, the dimmer it appears to be. So before we can actually really say for sure how bright a star is, we kind of need to know how far it is first, right? Maybe we should start there. Okay, so if we're going to start with distance, and indeed if you were an astronomer whose job was to find any of these 5 major characteristics about any of these stars, how would you go about doing it, right? Especially if, this is something that's never really been attempted before. If you were one of the early astronomers, a few decades ago or whatever, who was assigned to try to catalog all the stars in the sky, what do? Well, for distance, for nearby stars, it's actually somewhat straightforward. If you look at any object in the room that you're sitting in right now, and you kind of put your thumb over it, like right up next to your eye, right? You make your thumb cover it. You bring your hand right up to your face and you make your thumb cover that object. Let's say, we're talking about the D in distance there, right? Okay, now if you close that eye and you look at the other eye, what happens? It looks like your thumb is way over here now, right? Put your thumb over an object, bring it right up to your eye, and then switch eyes. It looks like your thumb has moved a whole lot, right? Why is that? Well, your thumb was all the way up to one eye, and when you open it, it looks like your thumb is all the way over here in front of your other eye, because it is. Okay, now look at the same object, extend your arm to its full length, and now put your thumb over it, and then switch eyes. And this time it'll only look like your thumb has moved over like a little bit, right? Why is that? Because while the lateral separation may be the same, obviously objects that are farther away appear smaller, just like the distance between two objects appears smaller if it's farther away. We call this phenomenon parallax, and the lateral separation between your eyes is exactly why you have depth perception, right? If your two eyes were right on top of each other, if you were a cyclops, you would have no depth perception. But imagine, if you will, here's the sun, and here's the Earth's orbit around the sun, right? Now, if we were to look at some star, and we wanted to figure out how far away it was, and we took its position relative to a bunch of distant background stars, and we took a picture of this star in, say, January, and it appeared to be here, right? And then 6 months later, when we're all the way on the other side of the sun, right, halfway through our orbit, we take another picture of this star, and it appears here, next to very distant background objects, really, really distant stars, galaxies, things like that. And this separation, this apparent separation, will tell us how far this star is from us. Okay, we call that parallax, spelled like this. P-A-R-A-L-L-A-X, parallax. Now, for stars, because even the closest one is something like 4.3 light years from us, it's really, really far, right? So it's, 4 times the extent of the very, very edge of our solar system, like way beyond the Oort cloud, out where, like, the sun's gravitational influence finally ends, right? It's like 4 times that. It takes light 4.3 years to get here from our nearest neighbor star, Alpha Centauri. And so this is kind of not drawn to scale, right? If this is 1 astronomical unit, this would be 50,000 astronomical units. That's really, really far. And so the angle that we would measure here, right, this angle wouldn't be like 60 degrees or whatever. It'd be almost 90 degrees. The angle would be off by not degrees, but less than that. So if we take one circle, right, we can divide that into 360 equal pieces, and those are called degrees. This is 1 degree. Okay, and then if we took this 1 degree and we split it into 60 equal pieces, those are what we would call an arc minute. With me so far? Okay, and if you took one of these arc minutes and you split it into 60 equal pieces, you would have, I'll write the abbreviation for it up here this time. This would be an arc second. Okay, now, obviously, the farther away an object is, the less it's going to look like it's moved compared to distant background stars. So the farther away something is, the less measurable parallax there is going to be. If an object is 1 arc second, or displays 1 arc second of parallax, the distance from here on Earth, where we are, right, Earth orbiting the Sun, the distance from us to an object that is 1 parsec, or has 1 arc second of parallax, right? This word comes from par, or parallax, and sec from arc second, right? So the word parsec means 1 arc second of parallax. And an object with 1 arc second of parallax has a distance of 3.26 light years from Earth. Now, if an object has less than that amount of parallax, it's farther away, right? Usually we say something like distance is 1 over parallax, or parallax is 1 over distance, if you want to keep it proportional, however you want to write it. But let's say that if your distance is 1 over 1 arc second, right, that'll give you 1 parsec, right? But then if you have 10 arc seconds of parallax, the distance is not 10 light years. It's 1/10 of that, 0.326 light years. If an object has 1/10 of 1 second of parallax, 0.1 arc seconds, then it's 32.6 light years. Okay? So the less parallax there is, the farther an object is. The more parallax there is, the closer it is. Just like if you put your thumb over your eye, right, and you bring you put your thumb over your eye right up to your face, when you switch eyes, it looks like your thumb moves a lot. But if you put your thumb over an object, at the end of your arm, it looks like when you switch eyes, it moves, just a little bit. The farther away things are, the less parallax there is. Okay? Now, obviously this technique only works for stars that are close to us. There are stars that are far enough away that we can't tell how far they are by parallax because we're limited by our technology, right? However, as you'll see in the coming weeks, for objects that are farther away, we can use what we call spectroscopic parallax, because stars all have a very specialized kind of radiation that they give off. Also, if they're really, really far, beyond even our ability to take a spectra of a single star, right? If you're talking about like another galaxy, we can't really resolve individual stars in distant galaxies quite so well. Again, we're limited by our technology. However, if we are looking at a galaxy that's really far off. Sometimes we can use what we call a standard candle, like a Type 1a supernova, because Type 1a supernovas all happen for the same reason, they happen the same way, and all have the same incredible brightness. And so if we know how bright they are, we can kind of figure out how bright they should appear and then compare. Okay, so that's distance. Arc seconds and parallax and all that good stuff goes into distance for the closest stars anyway. For the farther ones, we'll use other things like spectroscopic parallax and standard candles, but we'll come back to that. Okay, now, the next one, next simplest one, appears to be brightness maybe, right? Because if we actually can figure out how bright or how far an object is, and we know how bright it appears, we should be able to figure out how bright it actually is. Just like if we see a couple of lights, you know, a little ways away, but we know how far it is because we can kind of see it moving, or there's a landmark near it, or something like that, then we can tell how far away it is. And because we know how far it is and how bright it appears, we should be able to figure out how bright it actually is. Like if you look up the road and you see that there's like a telephone pole or a radio tower or a building that you recognize or something like that, and there's a couple of lights next to it, you can probably puzzle out that they're headlights that belong to a car, right? If you know how bright something appears to be, and you compare it to its distance, you can figure out the actual intrinsic brightness of an object. Now we've, you know what, we'll go over the distance, the difference between these two first. We've been able to look up at the stars for a very long time. And so we've been cataloging the brightness of objects for some time. However, we haven't always known how far the objects are. And so we put together a scale for brightness. We call this magnitude. And the magnitude scale basically goes something like this. If there's an object in the sky that's magnitude 0, right, that's kind of our basis for comparison, is the number 0. There was basically one object that we call the 0, and that's the star Vega. It's one of the 3 stars that make up the summer triangle of Vega, Altair, and Deneb, right, those 3. But it's a very bright star. It's not like stupid bright. There are a couple stars that are brighter, Sirius and Canopus, for example, and then of course our own sun. The sun is very, very bright. But let's say that there's a star that's brighter, right? Somewhere on this scale here. And here we'll call this +1, right? +1 would be like the star Canopus. And here at 0 we have the star Vega. Now, Canopus being +1 is 2.5 times brighter than Vega. Okay? And then here we've got a -1. And that, a good example of that is the star Spica. Vega is 2.5 times brighter than Spica. So how many times brighter is Canopus than Spica? Well, you got 2.5 times 2.5, that's actually 6.25, right? The North Star is a -2. This is Polaris. So Vega is 6.25 times brighter than Polaris, and Canopus is about 15.7 something times brighter, right? 2.5 times 2.5 times 2.5 times brighter, and so on. Obviously, there are brighter objects than this. There's the moon. The sun, of course, I think is -26, I want to say. It's the brightest object in the sky by a whole lot. The moon, I think, is shoot, somewhere between positive 12 and positive 14, I think. But the moon, of course, is much brighter than any of the other stars because it's closer to us, right? So distance is a key factor there. Obviously, the star that is brightest in the sky at any given time is the sun, and it is much closer to us than any of the other stars, right? And so distance is very quickly becoming a very important thing. So this magnitude scale, I mean, we've been cataloging things for a very, very long time, and so we didn't kind of want to just throw it out. But we realized that this magnitude scale only accounts for how bright things appear on Earth. And so this magnitude scale is what we call an apparent magnitude scale. This is how bright things appear from our home here on, whoops, looks like a flag of Denmark or something. Here we go. From Earth. Right? Now that is different from how bright one of these things actually is, right? The intrinsic brightness of one of these objects, which is another matter altogether. The actual intrinsic brightness of an object is something that we call the absolute magnitude. And that's how bright something would appear not from Earth, but from a reference distance, a fixed distance of 10 parsecs. And if you remember your mathematics, 10 parsecs is roughly (32.6 light years, right? Because 1 light year is about 3.26, or 1 parsec, excuse me, is about 3.26 light years. Okay. So, now that we've gotten the brightness, this will definitely be on the exam, by the way, the difference between absolute and apparent magnitude. So make sure you know those. Make sure you understand that the difference between one order of stellar magnitude is about 2.5 times. Okay? All right. So we talked about brightness and distance. What's next? Well, solving for the massive stars isn't super easy, but we can see the light from all of these stars, and we actually have a pretty decent understanding of how it is that the light from other stars works, because we have a good understanding of electromagnetic radiation as it is. So, maybe we should look at the color or the wavelength of the electromagnetic radiation that comes from these stars. So we need to remember two very key things if we're going to talk about the frequency of light or the color of starlight. That, of course, these two things are, of course, Wien's law, or Wien's displacement law, and also the Stefan-Boltzmann law. Wien's displacement law, if you remember, just says that the hotter an object is, the bluer the peak color, the brightest color from that object is going to be. That's pretty straightforward, right? And then the Stefan-Boltzmann law, let me see if I can remember. It was something like B is equal to lambda, you know what, forget it. The Stefan-Boltzmann law says that the luminosity is proportional to temperature to the fourth power. And what that means is the hotter an object is, the brighter it's going to be. Right? That should be pretty straightforward. Also remember that different elements when excited, like if you have hydrogen gas or helium gas or whatever, when the gas gets excited, they will give off different emission colors owing to the quantization of their electron orbitals, right? Because as these electrons come back down, they have to emit exactly the energy difference in between these states, and so they'll give off only certain colors, certain frequencies, certain wavelengths, whatever you want to call them, of electromagnetic radiation or light. Okay, so that's just catching us up to speed now. Also remember that if you have a star, right, you have a star like our sun, the sun has an atmosphere, right? And as it radiates tons and tons of heat energy or whatever, generally you have essentially light of every possible wavelength that comes up from the surface, but then that is going to heat up and excite the gas in the atmosphere, and just the wavelengths associated, or frequencies, whatever you want to call them, associated with the emission lines for the gases in the atmosphere of that star are going to get scattered in all directions. And so the light that gets through looks like a continuous spectrum with those emission lines missing. And those emission lines, of course, will tell us what the atmosphere and therefore the star is made of, right? Because this star, and if it has, planets and an Oort cloud and whatever, all that stuff are going to be made out of the same cloud of material, the same nebula or whatever that made it up, right? Okay. Now this tells us a few things. We've been able to look at just about every star that gives off pretty much every kind of light. As a matter of fact, we've been doing astronomy in the infrared and ultraviolet and X-ray and all that stuff, and it turns out actually that black holes are the brightest objects in the universe at the X-ray portion of the electromagnetic spectrum. But for most stars, just about all of them in fact, the brightest colors that they give off are in the visible range. And that's actually really no surprise, because our sun is kind of in the middle of the distribution of stars. It's not the bluest or the hottest, it's not the smallest or the reddest and the coldest. It's kind of somewhere in the middle, right? And the color, the brightest color that comes from the sun is like in the middle of the visible band. And so, some stars are hotter, some stars are colder, but we can kind of see them all with our eyes pretty easily, right? Also, this may be news to you, but the single brightest wavelength of light from the sun is 550 nanometers green. And it's for that reason that all plant life on the surface of the earth, because they undergo photosynthesis in order to take their energy from the atmosphere, from the environment, excuse me. Although some of that does come from the atmosphere, they get their carbon dioxide, right? But plants have evolved in order to take their energy from the environment by photosynthesis, and therefore light from the sun. So it's really no surprise that the single brightest color is everywhere here on the surface of the Earth, green. Okay, in any case, if you have a look at today's image bank, there's an image of Wien's law and the Stefan Boltzmann law. But suffice to say that stars, all the stars that we've looked at, they all have a peak somewhere in the visible part of the electromagnetic spectrum, right? And so essentially, stars that fuse hydrogen into helium have a very telltale spectral signature, right? Now, if we look at the light from a star, and it doesn't matter if it's peaking way down here in the red, and so it's kind of dim, or it's really, really bright, and so it peaks over here in the blue. It's going to have like some kind of curve. It'll be brightest, like if it's our sun, it would peak like right here, right in the middle, right where green is. but it looks yellow because it's, there's more. If you total up all the red and orange and yellow, that's the brightest set of colors, and so that's why the sun looks the way it does, right? There's less blue and there's more yellow and orange. I guess Lucky wants to sharpen her claws, so we gotta let her do that. Okay. Where was I? Right. So because stars all have this kind of telltale spectral signature, if we look at a star and we're not sure of its characteristics or how bright it is, how far away it is, but we look at a star and we can read what its spectral signature is like, we know then how bright it should be, right? And if we know how bright it should be, compare it to how bright it looks, we can tell how far away it is. Right? We call that spectroscopic parallax, and that's what I was talking about earlier. In any case, some simple spectral analysis has clued us into one of the other key characteristics of starlight. Okay. What do we got left? We got size and we got mass. Mass is actually kind of... There goes Lucky. Mass is actually a little tricky, so we'll save that one for next time. So let's talk about the size or the radius of stars. Now we already said before that according to Wien's displacement law that a bluer star is hotter, right? And that's something we all have experience with. Obviously the hottest part of the fire is the blue part, right? But also, the Stefan-Boltzmann law says that for an object to have a bluer color also means, because it has a higher temperature, it's going to give off a lot more light per unit area, right? Just like if you turned on your electric stove, the hotter it gets, the brighter it's going to be, right? Wien's displacement law says that it's going to be blue in color, but the Stefan-Boltzmann law says that the hotter that electric stove is, the brighter it's going to be. But also, if you have a small stove, it's not, even if you turn it all the way up, it's not going to give off the same amount of light as the big stove, right? It has more surface area. And so the area, the surface area of a star also would be able to tell us something about the amount of light that it's going to give off, right? Its intrinsic brightness. Now, if we know how far an object is, and we know what color it is, according to the Stefan-Boltzmann law, we should be able to figure out how much energy it's giving off per unit area, right? That's what color is. Obviously, the hotter something is, the bluer in color, the more energy it's going to give off per unit area. However, let's say we look somewhere out into the universe, right, and we see two stars. They're both red, right? And we know that they're both about the same distance. However, one of them is much, much brighter than the other. What can we conclude? Well, if they both have the same color, then they should be giving off the same amount of energy per unit area, right? And if they're at the same distance, they should appear the same brightness if they're the same temperature, right? And also the same size. Therefore, we can only conclude that if you see two stars, they both have the same color, let's say they're red, and they're at the same distance from us, 10 parsecs or whatever. The only way that one could be much, much brighter than the other is if one is a much larger star with a much larger radius and therefore much more surface area, right? This could be the difference between, a small little red main sequence star and, say, a red giant, or possibly even a red supergiant. Thus, these four pieces together have already shown us tons and tons of the major characteristics of main sequence stars. We'll save mass for next time. Okay, and that about wraps it up for today. If you have any questions, please get a hold of me through the normal channels, and I'll see you next time.